Thank you for reminding. Yes, I had not completed the
Sir, I had a doubt. Like, uh,
yes.
is it okay to do the Z3 in Python, or like should we do it in this
No, 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 no.
language?
Any language. I mean, every time I offered this course, I've always gone, the students can choose whatever language that they want to program it in. And I think Z3 interface is available. Okay. The API is available. I think you should, upload the API interface. I'm not going to cover that in class. I mean, you could read it up. Now, for example, if you want to program the generation of constraints, what you'll have to do is you can do that in Python, okay? And the API functions provide, the API provides functions to construct formulas in the notation that you saw, the SMT notation. So that's a standard, okay, called SMT lib2 standard, okay? I mean, I keep using the word SMT. By the way, SAT solver, SAT stands for Boolean satisfiability. SMT is kind of an extension of SAT solvers to quantifier free other kinds of, even to first order, okay? SMT stands for satisfiability modulo theories, okay? So just imagine that you have Boolean, first order formulas over multi-sorted logic, okay? Which has, besides Boolean, you have numbers, real, reals, natural numbers, and other kinds of data types. And that's what SMT is. And usually, nowadays, SAT solvers come as part of packaged as SMT. So Z3 is actually an SMT solvers. So if you went through the guide, the first few examples in the tutorial starts with examples over that have, constraints over numbers, okay? Reals and so on. So, there are just like DPL, the SAT solvers, the DPL algorithm, they are decision procedures for propositional logic. You can have decision procedures for fragments of other theories like natural numbers and so on. So that's another course that I teach called SMT solver and its application to various things, including software engineering and what goes into SMT and so on. And these days I teach it for an application that is gaining more and more attention, mainly to deep learning. Okay, and I will be offering that not next semester, but the semester following that. No, next semester itself. Yes, so I'm looking at one of the things that I'm doing as part of my research is to apply these techniques for verifying machine learning algorithms, and a lot of there is a lot of interest in that application domain in industry. But in any case, so I'm digressing. So as I was getting back to it, this pigeonhole problem is something where for which the best SAT solvers don't seem to perform very well. And you can see that once you have this, you can it's soon for very small numbers, and it'll hit the NP hardness bottleneck. Okay. To that extent, also the size of the formula, the number of constraints. So SAT solvers, the complexity is measured how hard it has to work is measured in terms of the number of variables in the formulas. That is one measure. And the other thing is, usually that is the measure that is used for thing. And the other one is the number of constraints. Okay, so specifically the number of clauses in the number of clauses in the CNF notation. So these are the two things. Now, pigeonhole problem, when you model it, you will see that the number of clauses is not very many at all. So even for a small set of clauses, for beyond even a small number n of variables, here the n is the number of holes, it hits that bottleneck. So this is something very has puzzled complexity theory people for a long time. This is NP-hard. This is an NP-hard problem, because people don't know. There's no existing algorithm that can solve it in P. But yet there are so many problems. Some of them very practical, for which it is so efficient. Okay, so why is this so? Is a subject matter that that complexity theorists have been looking at, and it seems that for Boolean satisfiability, there are what are called islands of tractability. Okay, so there are some structure, if the formulas or the problem instance displays certain structures, so there are certain isles of tractability that if your problem instance problem false is an instance inside that falls inside that island, then it is very efficient. Okay, and the complexity of a real problem, there are people who have defined measures how far your problem instance is the distance from the isle of tractability of the problem to your problem. To your problem instance, and depending upon that distance, it gives a measure of how hard a particular problem. So SAT solving is not only of interest in its application to verification and so on, but it is also a subject of interest for complexity theorists as well. So as a first assignment, what I want you to do is just take small instances of this pigeonhole problem and the NBOR problem, try it out, okay? And I might even give you an even smaller problem, okay? And I will send it by email that you will certainly be able to do by hand, and try it out on the thing. And also write a Python program to generate the constraints using the API. Okay, that's the second part. Now, the API, I will give you, I will point you, you can do a Google search and you will get the API yourself for Python. So I will let you, read on your own the interface and generate the constraints for these problems using the API. So when you use the API, it provides you functions for constructing these formulas and then dumping it into a file, and you can then submit the file which has all your assertions and so on. So that, what you're typing in the interactive mode yourself into a file, and you can upload that file to Z3. That is one way to do. Or you can even call these functions sat check, get model, etc. as in your Python program itself, and display the model as well. Okay, or dump it into a file. So that is how you do things when you want to develop applications, either to solve problems or to do a verification, whatever, to using SAT solvers, or more generally SMT solvers. Okay, so that is you can consider that as the first assignment that I'm assigning. Okay, so let's see. So I won't discuss a solution for Sudoku in this class, and I will let you, as part of the first assignment, solve the 8 queens problem and another small problem that I will send you, and the pigeonhole problem. Okay. So, what are the constraints? I first want you to, if you thought about it, I want, if any of you has thought about it, I want you to give your thought. So what are the constraints that you need? I am assuming that you know the rules of Sudoku. Any?
Yeah, in each cell, a value should be specified from 1 to 9.
Yeah, that is already,
Exactly.
That constraint is already done. I'm asking for other constraints.
So if we are specifying a value in a cell, then that row must not contain the same value again. Same
That's
goes
right.
for the
So
column.
yeah, in every row and in every column, a particular number has to appear uniquely, correct? So there are 9 positions in a row and 9 columns. So every number has to appear uniquely. Okay, that is one constraint. That has to be the case for every row and every column. Okay, that is one set of constraints, correct? What is the other? There is an additional constraint as well, right? That should hold good for each grid also. Each 3 by 3 grid in your, and there are 9 such grids here marked in with the dark boundaries. The cells in each of those, the numbers have to appear exactly once in each of those grids. Okay, so that is, those are the constraints. So here, what it is. So each value must be used exactly once in each row. For each row I, it says that exactly one of these variables has to be true, where J and K will be. There will be 9 times 9, 81 such constraints. Okay, and each of which is a summation of 9 variables. That's how you should read this thing as. Okay, so when you sum all those 9 variables, it should be 1. So there'll be one such constraint for each I ranging. For each row it will be this constraint for each J and K. Okay. And similarly for J, okay, with ranging over I and K. Now, and each value is used exactly once in each grid. You can do some clever index expressions. Okay, so for each S and R, you can specify each grid using the indices for the elements in each grid can be expressed by these expressions 3i times r and j plus s, where r and s range from 1 to 1 to 3, and by that kind of way of systematically enumerating the indices of the cells in each of the grids. And here the R and S are chosen as the coordinate for each of the grids. So 1, 1 is the top left, and 3, 3 is the bottom right in a grid. Okay, and that's how this index is expressed. And then you will require that the summation in each of them has to be exactly 1, which expresses the constraint that each number from 1 to n should appear uniquely. Okay, so here I've expressed these things as summation over numbers. Okay, I mean summation to be equal to 1. How do you express? After all, you can't use numbers like this. Okay, the numbers 1 through n, they are they are thrown away. Although they're used here, they appear actually as part of the names of the variables. Okay, but this summation, how do you encode that in propositional logic?
Summation is OR operator, right? So we can.
Correct, but I'm requiring exactly 1. Okay, so yeah, summation can be encoded using the OR operator, but here I'm requiring that sum to be 1. Okay, so it has to be translated, encoded as you did for exactly 1. Okay, so if I had 2, then it would be at most 2, kind of a thing. Okay, or less than or equal to 2 will be at most 2. If it is equal to 2, it will be exactly 2, exactly 3, and so on. Okay, so since I have it to be 1, it has to be encoded as someone prompted exactly 1. So this we have already seen, right? So here at least 1 xi has to be true, which can be encoded as an OR, and no more than 2 should be true, which can be encoded in this fashion. Okay, so your generation algorithm, once it generates this thing, it has to then generate it like this. Yeah. Okay. Yeah. So using SAT solvers to model these things, any particular domain, in this case it's a game, is first you'll have to think about what how you choose your variables. Okay, and what exactly they represent in the problem that you need to solve at hand. Okay, and then you have to think of what the constraints that you want to express are. So if it is something modeling a game or a board game, then it is what these constraints will encode the rules of the game. Okay, and then there is a encoding problem, how exactly you encode each of these constraints in propositional logic. And as part of that, sometimes you need to you have to think in terms of schema, like I've done here, by using some aspects of the problem as the indices of the variables. Okay, so that will also be important. And then once you have the schema, then you could write a program, and all those conjunctions will, all the constraints, each of those constraints, a conjunction of all those constraints will be your encoding of the solution for the game or the problem as a propositional formula. And any satisfying instance of that, if there is one, will be a possible solution. Okay. Any satisfying instance. That's how you think and encode the problem. Okay. Any questions?
Sir?
Yes.
In Z3, do we have to input every formula in exactly CNF form? Because Z3 seems like a more powerful language. It accepts some real numbers.
Yeah. So there are actually, that's a good question. See, SAT solvers do operate like DPLL. You have seen DPLL. DPLL algorithm assumes that the input formulas are in CNF. Okay, but SAT solving tools allow you to input your formula in any form. Okay, in the sense that they define connectives. Okay, all Boolean connectives, and you can write your assertions like when the formula inside the assert command that you type in to Z3 allows you to express the formula, that is the argument to assert, to use any connectives. Okay, that is at the user level. You don't need to encode it as the thing. I mean, if these formulas that you represent, you could use any connectives and don't worry about when you input it to Z3, because the syntax of the formula is that it accepts any connectives. Okay, so from a user's perspective, you don't need to worry about the having to encode it as CNF, because that is done by the interface to the SAT solver. Okay, before it ships it to the core algorithm, the SAT solving tool will do the conversion. But what I don't know if you raise that as part of your solution of a problem, but an interesting question that poses is, given any Boolean formula, if you try to convert it into CNF, what is the problem? There is a problem. Can you say what might be the problem? If you were to do it, I mean, obviously SAT solver also internally does it, okay? Because the algorithms work on only formulas that are in CNF. What happens when you try to convert an arbitrary propositional formula? When I say arbitrary, one that uses other connective like exclusive OR, implication, equivalence, and so on, or negation. Okay.
The number of variables might blow up.
No, the number of variables is the same. Okay. Suppose given a formula that uses a certain number of variables. Okay. You have to get rid of, when you convert into CNF. A CNF is something that uses only negation or an and, correct? And that too, the negation. Look at what the form of CNF is. Yeah. So here, a CNF is a product of sums, and it is in a form in which the negation can appear only at the atomic level. Okay. For instance, you cannot have a complete clause negated. Okay. So that's what CNF is. So the three concepts. One, it can be a conjunction of clauses. Okay, that is one constraint, and the negation has to appear only at the atomic level. That's what determines that a particular formula is in CNF. Okay, and such formulas where the negation can appear only as at the atomic level, at the literal level, they are called negation normal forms. Okay, and CNF and DNF are instances of of negation normal forms, where the negation can appear only at the leaves. Okay, so when you try to do this, I think whoever's pointed that thing out, the number of variables, formula, whether you express it using other connectives, the number of variables will be the same. But when you try to convert them into, try to push, if the negations, for example, appears at the top level, you have to use this De Morgan law, right, to push the negation all the way down. And then you have to, in order to get it as a conjunction of clauses, you will have to distribute the conjunction over ors and vice versa. Okay, both those application of De Morgan, the act of pushing the negation down, as well as distributing ads over R, will cause an exponential blow up of the size of the formula. Okay, maybe that's what you meant. Okay, so the number of clauses will can increase exponentially. Okay, when I said the size of the formula is measured in terms of the number of variables as well as the number of clauses. Okay, actually the number of clauses is also very important in our compliance. That will exponentially grow. Okay, therefore you can ask the question, how does SAT solver even manage this? If you allow other Boolean connectives, just the act of converting them into CNF itself can blow up. Okay, your problem itself will end up blowing up. I will later on in one of the next few courses, there is a clever trick that you can use to encode all an arbitrary connectives without actually expanding them out using these distributive laws, etc. There is a way to encode. If it's called Citon encoding, and we will discuss that. And that's what SAT solvers use at the interface. If you allow for a linear number of increases, linear number of increase in the number of variables, you can avoid the exponential blow up in the number of clauses. Okay, there is a very clever encoding that you can actually do, and that is due to a guy called a logician called Citon, and we will see. I will show you that. Okay, and that's what I'm taking this occasion to point out an aside for this thing. So how you get around the problem of avoiding exponential blow up at the interface itself. Okay. What did I?
Actually, we saw Sapiens construction in the logic course.
Oh, you did? Oh, okay. So that's good. So Narayan Kumar is doing a lot of the things. So then, yeah, okay, that's very good. So that is thing. So I'm glad to hear that. So that's how you do. Okay, so you don't, if you really at every level of the formula, you try to eliminate that by using the laws, De Morgan law, you will get an exponential law. Okay, so and you saw that the Citon encoding, it uses additional variables, and the number of variables is linear in the size of the formula. Okay, by size I mean the number of connectives. Yeah. Okay.
Yeah, for each branch.
Correct.
new variable will be there.
Exactly right. Good, good. Yeah. So that's what SAT solvers use. Yeah. Okay. Good. So I'm glad to hear. So who's that? Who answered that?
I'm Amin.
Amin. Okay. So the other two people, they you understand it. Now I want to make sure. Okay.
Yes, sir.
Yeah. Yeah.
Yeah,
Okay.
we
We all took a logic course.
Yeah. Yes.
we all took
Okay.
the-
Good. So you already. I'm glad that you've seen that. Okay. That's how that you do. Okay. Good. So yes, that's there is QBF that I will get to later on, quantified Boolean formulas as things. So we will also be using just simple proposition logic and then quantified Boolean formulas. But before I introduce quantified Boolean formula, I mean, this is proposition logic with quantifiers where the quantified variables are ranging over our proposition variables. Okay, and there are advantages for using QBF to using quantifiers, although quantification over propositional variables can be easily gotten rid of, right? Okay, because you can expand them out, because after all, there is a case for 1 and there is a case for 0, the variable taking 1 and 0. So you really you're not adding any logical power by introducing quantifiers over finite domains, but your formulas will be, if you use quantifiers, will still be exponentially more compact, okay, in terms of the size, and therefore there are advantages for modeling and so on. And then there are SAT solvers that can directly deal with these quantifiers. That is, we will get to that later on. But what I want to do today is introduce you to, although I've given you a course description, I'm not, what is the course about? What is the learning outcomes of your course, of the course, and so on. So I want to and kind of motivate you if you're not already motivated with what I've seen. So this is the introductory slide that I. Okay, so that's what I want to do. Okay, so before I move to this introductory lecture that gives a little bit more idea of what is the focus of this model checking course, are there any questions about what we have seen on SAT solvers or the modeling? Do you have any questions? Okay, so I'll assume that it's a no. Anyway, so nowadays you see what I call as embedded systems. I keep using computational systems. I mean, what I really mean is embedded systems, and these these embedded systems can have hardware, software, and some firmware. Okay, so this firmware is some combinations. It's really a software that it's a low-level software. The high-level software is kind of the application level, which is written in Python, C, and so on. Firmware is something closer. So a combination of these things is what make what is typically called embedded systems that control various operations in much larger systems, which involve a lot other components, electrical, mechanical, components that control various aspects of systems, complex systems such as trains, cars, and whatnot, aircrafts, and so on. These things typically interact with an environment, okay, where the environment are the inputs. So they are the outputs of sensors that actually sense various things. Output now, for example, it could be velocity, it could be, if there's a brake that you're applying, it could be, some tension things and so on. So various things that are important that the sensors monitor from the environment. And every time the environment changes, these control software, not software, the control systems that have a digital component to it, they react to the changes in the environment and they activate. They produce certain outputs that go and that are used to activate or certain other components. So what is of interest is, and what is critical is in assuring that this embedded system, which is a combination of hardware, software, and firmware, is safe, that they don't violate certain safety rules, don't get into certain states which it is not supposed to get into, okay? And that is the main aim, and that is the impetus for these model checking and various other methods that are used to provide this assurance. And as you can see, the more systems, the more electronic and embedded components that you have in your systems, the more critical it becomes for you to ensure the safety. And that's why companies are willing to invest a lot of money into technology that can give a very high level of assurance to these embedded systems. Okay, the traditional methods, are simulation and testing, and that you can never completely get rid of that. So people do use simulation testing, but they have their limits. They do not guarantee 100% coverage. Therefore, they're also quite expensive. You have the entire setup that you need, and especially if it is an embedded system. If it's just testing software in isolation, you can just run the software. Even that is time consuming in terms of if you want to get 100% coverage. But when you have all these other mechanical and other components, building the environment itself becomes expensive. So the real question is if you can have methods that guarantee that you can guarantee 100% coverage without actually running all those tests, okay, like you would do in traditional methods. And that's the subject of formal verification. One such technology is model checking. Okay, these methods are based on logic and automata theory. Model checking is one such popular technique. Okay, and this was invented. At least the credit goes to these three folks who got a Turing Award for it. That is the citation. These three people that I've listed here: Edwin Clark, Emerson, and Safakis. And Clark is no more. He just passed away 3 years ago, and he was at CMU. So that is just a bit of history that I give. So what kind of systems and properties? See, there are, this concept of formal verification is, it can be used to all different kinds of systems, and the exact mathematics or the logic that is required, of course, depends on the kind of systems. So at least for this course, we limit our focus to certain kinds of systems, which are called which is they are discrete systems. So I'm showing examples. We can also apply it to systems like cyber physical systems, where the data, the types of things that range over continuous data, then you will need a different kind of you may need a different kind of mathematics. So that's why I'm going to be showing you the kind of model checking techniques that we will be limiting ourselves to in this course can address these kinds of systems. And then another axis is also the kind of properties that you want to verify. Okay, both these have to be scoped or restricted appropriately, and the kind of techniques very much are dependent on what kind of restrictions you put. Now here, for example, is control software for that's controlling the traffic controller. Okay, and the kind of properties, so you want to be able to, the modeling formalism that I will be introducing, I want it to be able to model the control logic of this kind of systems at an appropriate level that we can then use to analyze and ensure the traffic lights should never be green at the same time. Okay, so if it's a green, then you know that is can lead to bad things. Okay, so this is the kind of systems that we focus on, and the kind of properties. Okay, or my system can be a kind of hardware. Okay, which is built as a network of gates and flip-flops. Okay, and it can be asynchronous hardware, means that it is being controlled by a clock. So then you might want to prove the counter value, so which is stored in these registers AB, is always less than or equal to 3, and there are even more complex things. Okay. Yeah. Now, for example, here, these are called, that something bad never happens. They're called safety properties. You can also have progress properties, okay, that eventually, if the signal is red right now, eventually it becomes green. Okay, so there is progress properties. They are called progress properties, that you won't get stuck in some state. Eventually, something good will happen. That's the kind of properties. Okay, or your system can be, so in this, it can be pure software, okay, written as say a code, and then you might want to check whenever I'm at line 3, y is always greater than or equal to 6. And I was again at line 3, which is at the head of the loop, x is equal to 0 holds infinitely often. So these kinds of things is what I want to be able to do. And my system can be, there are other kinds of things is where you have concurrent programs, okay, which multi-threaded concurrent programs. So here you might want to check the program has no data races, okay, that the synchronization is such that you will always get deterministic output, regardless of which schedule that you use, which threads you use, these which schedule you use to schedule these threads, you will have an deterministic output. These are the kinds of systems that we want to be able to model, and the kind of properties that we want to prove. Okay, we will formalize all these things as we go along in the course. Here I'm just giving you to give you an idea, okay, of what we're aiming at. Okay. What kind of systems we do not deal with? Okay, for example, you could track the actual motion of a pendulum, and then you want to prove certain properties over its behavior, and there your model itself will go into a continuous domain. Okay, and you will need your modeling techniques and the mathematics that you require will need to deal with continuous variables that range over continuous data. And your notion of time will also be more real time, okay? And that is something, kind of systems that we don't deal with. Although there are model checking algorithms that do deal and modeling methods, as well as model checking algorithms that can do these things. For example, I don't know if you've heard of there's something called hybrid automata, where the variables over which it's defined some of them are discrete, some of them can be continuous, which are guided by partial differential equations, okay, and their motion. So there are techniques that combine these two things. But in this course, we'll only be sticking to discrete things, okay. So what we need is then a formalism. Yeah, what do we need to even do formal verification? These three things you do need, regardless of whether you're using model checking or other techniques, okay, for formal verification. Formal verification is what I've defined as something you're given a system or a model of a system and a set of properties. And what you want to do is it should give that method, it's called formal verification, if for all possible inputs and for all possible behaviors that the property is guaranteed to hold. That's what defines, distinguishes formal verification from simulation and testing way of assuring, okay? Model checking is but one method. That's what I want to stress. But for all the, regardless of the methods, what is required as inputs for this formal verification are the following. You need a common formalism to model all the systems of interest, okay? And what we will be defining, what I'll be defining is something called transition systems. This can be used to model the kind of embedded systems that we are talking about, okay? And it can be pure software, it can be pure hardware, or it can be a combination of things. And we will be describing this as a language or a formalism for describing the models, okay? And we'll be attaching mathematical semantics, precise semantics for the behavior of these models, and that's the important thing. And you need an expressive logic or language to specify the desired properties, okay? Here that property specification language can be special purpose logics called temporal logics, or they can even be automata here, okay? Certain special kinds of automata. And the one that we'll be talking about will be something called Buki automata, which your specification can be expressed in terms of those automata as well. Okay, and then what is the real problem of formal verification? I mean, when expressed formally, is given a model and a property in a particular language or logic, it is the model checking is an algorithm to check, or it is a bunch of techniques and algorithm, what have you, that checks if the given model satisfies that property. M satisfies the property. We've already seen this symbol, okay? So for propositional logic, propositional logic could be our logic of choice for capturing the specification, in which case my model there will be quite simple, which is just assignment to those variables. Whereas here, our model will be more complex and will be an instance of a transition system. And as you will see, that these things will have, the behavior will be a lot more complicated, and therefore you need a more complex logic to specify on the constraints on the behavior of the transition system. So these are the three things that will be the subject matter of the course. Now, before I get into model checking, so I just want to, in one slide, I've been saying model checking is but one method, okay, of for doing formal verification. What are the other methods? Okay, a very popular method. I mean, popular in terms of the number of how widely it is used in practice. Okay, that's how, I mean, when I say it's popular, is one something called static analysis, or more technically, it is called abstract interpretation. Now, this one is very automatic. It's push button. It's very scalable, and it is very widely used. Okay, but it is imprecise in the sense that it can give you false negatives. It can say that the system is, doesn't satisfy a property, when actually the system may not be violating, in the sense that the result it produces could be spurious. So these abstract interpretation techniques, they are sound, but they can give you false negatives. It never says when if there is an error, it does not say it is safe, okay, but it errs on the safer side. So it compromises precision for scalability, okay. There are techniques that there's a whole bunch of things, and then at the other end, these are very automatic, but they are imprecise. And the other end is theorem proving. It is very general. I mean, this also, by the way, static analysis, almost all of them, they restrict the kind of properties that they can actually verify. It's very, very restricted. It's even more restricted than what you'll see that model checking is capable of doing. The other end is theorem proving. It's the most general, both for expressing the kinds of systems that you can capture. As a matter of fact, the improving systems, you can use first order predicate calculus, so even more expressive logics like higher order logic and so on. And that kind of logic is used to both model, to encode your model, to develop your model, as well as your properties. But here, what it is, it can give you a very precise thing, but it is mostly interactive in the sense it's not push button, it's not automatic, but it does not put any restriction on the thing. I mean, these logics are so powerful that they support that they can actually describe more than what programs can actually do. In that, what I mean by that is, that first order predicate calculus, you can make up formulas, which are not decidable. Okay. So model checking falls somewhere in between these two extremes, and there they once again the models that you can do are. Especially in terms of the model, is the same kind of a thing that abstract interpretation is used for. Although abstract interpretation is primarily aimed at code things, but where it differs is from abstract interpretation is this is also pretty much a push button technology. It's automatic, and compared to theorem proving, it's more automatic, and the kind of properties that you can express are a lot more expressive, but more powerful than what abstract interpretation can do. And whenever as long as your property is within that logic, which model checking works, it gives a precise answer. Okay, there's no question about imprecision, and this is still automatic. But the kind of properties that it is able to check are not as expressive as theorem proving, and that's that. And so in that sense, they are limited. But the properties that they can express may not capture every possible behavior of system, but they are interesting enough and significant enough that these tools that are based on model checking are very, very useful, and industry finds it quite useful, and that's where their interest comes. And it's a very active area of research. There are, like more than, 25, 30 conferences. I mean, you find it's very active area of research for pursuing your PhD and so on. And both in terms of techniques and how you scale it to practice, there are a whole variety of things. You can pursue PhD in this area, solving very theoretically oriented problems and very pragmatically oriented problems as well. Okay, so I think here is a brief outline of the course. We will first start with modeling systems. I said transition systems. They're actually called Kripke structures. And then we'll cover specifying properties. And we'll be introducing temporal logics. Then the actual algorithms for doing it. So I'll kind of intersperse that with tool exercises. We'll primarily be using USMV and CBMC. I don't think we'll be getting to SATABs. And then I'll be covering automata-based model checking. Okay, this is what I call symbolic model checking, two kinds of model checking. When you use pure logic for doing it, then it is called symbolic model checking. And then you can also express those things as your language, as well as your, model will be the same as transition systems, but your language of property can be automata-based, in which case you'll use automata-based model checking. After that, I'll cover some recent techniques that are done for scaling model checking problems using abstraction and induction. They are mature. These are techniques that have been developed in the last 15 years or so, but they have matured they're mature enough that they are being made part of the tools that are used in practice. And this is kind of the outline that I have. I mean, this is something, the usual grade distribution that I have. I usually have one or two quizzes, and the other one will be a small programming project. I mean, usually, either I have two quizzes or sometimes one quiz, and I make the other one instead of a final exam, just a programming project. So I will, and I think rather than starting what transition systems are, I will end here, and I will, in next class, I will introduce you to transition systems, the formalism for that we use for modeling our systems. So any questions?
I wanted to know about the reference book. So is it
okay. Actually, that's the next slide. Okay, so this is the book for the symbolic model checking part that I use. Okay, this also has automata based model checking as a chapter. There's one other book that I might be using some part of, which I have not included here, which I will upload the cover page. I don't have it as part of this slide, but this is the one that I'll be using. So an e-textbook, there are two copies in the library, which but there is an e-textbook version for which I had subscribed to. I will see if that subscription is still available. Okay, and you can actually, and I will share the login details for that. Okay, so you can actually then log in and use that. Yeah. For the other textbook, I think I have the PDF version. so I can share that. Okay, I made sure that that it is legal for me to share for people that are registered in a course at CMI. Yeah, that I'll be using mostly later on when we discuss automata-based modeling. This I will upload right away. Yeah.
Could you also upload the slides?
Yeah, I will do that, and so that I will do right away. So I mean, after the class, if I don't do it right away, yeah, and as well as the videos, yeah, of the lectures, we'll do that. Okay, thank you. I'll see you next Wednesday. So next week the class will have the same schedule. After I return to India, I'm hoping that I'm able to return to India because the way things are going in India, and I'm hoping that there'll be I'll have a flight to catch. Okay, so after that, our timings might change. Yeah. Okay. Okay, I'm going to stop sharing. I'm going to stop recording.